In this lecture video, we're going to look at the issue of model identifiability in the context of structural equation modeling. Here's an outline of what we'll be looking at in this video. First, we'll discuss model identifiability in general. We'll then look at identifiability in the context of structural equation modeling. We'll then see what we can do to help ensure that our structural equation model is identifiable. So let's take a look. Let's first talk about model identifiability in general. Consider a family of distributions denoted by script F, which consists of a collection of PDFs or PMFs with argument bold X, which is a multivariate vector of responses, and a parameter theta, which may also be multivariate, coming from a parameter space, which we will denote by kappa omega. Now, if the following condition, which says that f of x when theta 1 is the parameter is equal to f of x when theta 2 is the parameter for all x, if that condition implies that theta 1 is equal to theta 2, then the family of distributions script f is said to be identifiable. That is, the family F is identifiable if different parameter points in the parameter space correspond to different distributions. Mathematically speaking, a family of distributions script F is identifiable if and only if a one-to-one correspondence exists between the family of distributions script F and the parameter space kappa omega. On the other hand, if there exists parameter points theta 1 and theta 2 that are different, for which f of x when theta 1 is the parameter is equal to f of x when theta 2 is a parameter, and that equality holds for all x, then the family script f is not identifiable. In other words, if two or more parameter points in the parameter space result in the same exact distribution, then the family script f is not identifiable. And we often say that then it's unidentifiable. Now let's talk about the importance of model identifiability. Theories are framed in terms of models and model structures. Research questions are posed in terms of model parameters, relationships between these parameters, and their values. Each point theta in the parameter space kappa omega corresponds to a different scenario or reality in the context of a theory. One major goal of a researcher is to identify which reality is in effect in a particular situation, under a given set of conditions, or in a given process. In other words, identifying a parameter point corresponding to a model that best explains a given real-world situation. In empirical science, this requires obtaining sample data from the situation under consideration, the conditions of interest, or the process being studied, and then using that sample data to estimate the parameter point. When a family of distributions is identifiable, each distribution in the family has associated with it a unique parameter point in the parameter space. In this situation, for a given observed sample, each distribution in the family will have a different joint probability or likelihood associated with that sample. For a given sample, these differences in likelihood result from the different values of the components of the parameter point. Hence, when a family of distributions is identifiable, for a given observed sample, all parameter points are distinguishable by virtue of the different likelihoods they produce for a given observed sample. This allows for more effective statistical estimation of the parameter point as a whole and of testing hypotheses about particular components of the parameter point. When a family of distributions is not identifiable, for every observed sample, some distributions will be indistinguishable from each other because they produce the same likelihood for the sample. This is because for a given sample, the value of the likelihood depends on the parameter point. But if the family of distributions is not identifiable, two or more parameter points are associated with the same distribution, and so they produce the same value of the likelihood for that sample. This means that for every observed sample, some parameter points, which again correspond to different scenarios or realities, will be indistinguishable from each other from the vantage point of the observed data. Such a situation renders statistical inference procedures difficult, if not impossible, and perhaps even meaningless, since it's not even clear what estimation means when a given sample could result with equal likelihood from two or more parameter points. Statistical models consist of several types of components, including random variables and parameters. For a given joint distribution of the random variables in the model and a particular parameter point, there is associated with a model a particular distribution. The family of models therefore corresponds to a family of distributions. If the family of distributions induced by the model is not identifiable, then the family of models is not identifiable. Now, the good news is that lack of identifiability is a problem that results from an ill-conceived theory and or a poorly structured model. For example, a model that has been over-parameterized. Such problems can usually be alleviated by modifying the theory and or reformulating the model. Next, let's talk about identifiability in the context of structural equation modeling. Structural equation models typically have many parameters, and this can cause problems in terms of our ability to uniquely identify each possible combination of parameter values implied by the model. There is much more flexibility available to the researcher when parameterizing structural equation models than there is in other types of statistical models. And because of this, more care is needed in constructing SEMs than with other types of statistical models. When an SEM is not parameterized correctly, this can result in the SEM being unidentifiable. Therefore, identifiability is an important issue to consider when developing a structural equation model. Now, SEM software may not and probably won't alert you when an SEM is unidentifiable, but instead it will go ahead and try to fit it. Now, this can lead to estimation problems. For example, if the estimation procedure is iterative in nature, you may have a situation where the iteration just is not complete. It can also produce results that are somewhat meaningless, and you may not even know it unless you become aware of the fact that the model is unidentifiable. And so it's up to the researcher to make sure that an SEM is identifiable. Now, with respect to model identifiability, a given SEM falls into one of the following three categories. And this terminology is coming from the SEM literature. Under-identified model, a just-identified model, and an over-identified model. So every SEM falls into one of those three categories. Now, let's look at an under-identified model. And again, that is the terminology that is typically used in the SEM literature. This is also called an unidentified model, which is the terminology that we have used previously. Now, a model is under-identified or unidentified when two or more combinations of parameter values result in the same model. And that's what we've been saying previously. Because different parameter combinations can lead to the same model, the model is not identifiable and therefore unique parameter estimates do not exist. What would they be estimating? Now, a model will most certainly be under-identified when there are more model parameters than there are non-redundant entries in the covariance matrix. A model can be under-identified even if the number of parameters is no more than the number of non-redundant entries in the covariance matrix. Structuring an SEM so that the number of parameters in the model is no more than the number of non-redundant entries in the covariance matrix is therefore a necessary condition for an SEM to be identifiable, but it is not a sufficient condition for an SEM to be identifiable. And we're going to talk more about this in a subsequent lecture video. Next, we have just identified models. Now, this is also called a saturated model, which is perhaps more commonly used in non-SEM literature, for example, in the context of categorical analysis and things like that. The model-based covariance matrix perfectly fits the observed covariance matrix with a saturated or just identified model. Now, a just identified model can occur when the number of model parameters is exactly equal to the number of non-redundant entries in the covariance matrix. However, this is not guaranteed. Even if the number of model parameters is exactly equal to the number of non-redundant entries in the covariance matrix, it may be that the model is not just identified. It may be unidentified. Now, even if a model is just identified, inferences cannot be performed for just identified models because there are no degrees of freedom remaining for any kind of a test. All the degrees of freedom have been used up in fitting in, the model by estimating the parameters. Finally, we have what is called an over-identified model. An SEM can be over-identified if the number of parameters is strictly less than the number of non-redundant entries in the covariance matrix, although, again, this is not guaranteed. Now, inferences can be performed for over-identified models. A model is guaranteed to not be over-identified when the number of model parameters is greater than or equal to the number of non-redundant entries in the covariance matrix. Finally, let's look at what we can do to help ensure that a structural equation model is identifiable. Now, Raykov, in 2000, gave 6 rules for determining which components in an SEM are model parameters in order to help ensure model identifiability. And basically, these rules help to make sure that we don't over-parameterize a structural equation model. These rules are given on the following slides, but we need to keep in mind that these guidelines can help increase the likelihood, but cannot guarantee that an SEM will be identifiable. Rule number 1, all variances of independent variables are model parameters. Rule 2, all covariances between independent variables are model parameters. Rule 3, all factor loadings connecting the latent variables with their indicators are model parameters. Rule 4, all regression coefficients between observed variables or latent constructs are model parameters. Rule number 5, the variances and covariances between dependent variables and the variances between dependent variables and independent variables are never model parameters. And then finally, Rule 6, for each latent construct included in a model, the metric of its scale, that is, its standard deviation or its variance, needs to be set to a particular value. So that's what I wanted to cover in this lecture video. I'll see you in the next video.